Screen is visible?
Yes, sir.
Okay. So today we'll start a new chapter, that is torsion of a shaft. Now, what is shaft? Shaft is a circular cross section which is having a length. It may be either solid section or it may be a hollow cylindrical section. And torsion means we want to say that if this shaft is acted by some twisting moment here, say in this direction, the moment twisting moment is acting this anti-clockwise, and if this portion is fixed to some fixed end, so here at this case the reacting moment will act in this opposite direction. So when this twisting moment, so this is, if we say at twisting moment, if it is acting in this direction, so it will try to rotate this shaft along with this direction. That means whatever, if we say this is the original position, this is say a outer line of on the surface of this shaft. Due to this twisting moment, the tendency will be this position will try to go some new position, say here. As this portion will remain fixed, so here it will go like this, and from this figure we understand that due to this change in dimensions, it is the only the length is changing and the position of the initial part is changing to a new part. This induced some sort of shear stress in this whole section. So when some twisting moment acts on a circular shaft, it creates some sort of shear stress. So today we will see how the twisting moment is acting on a shaft, and for that reason how the shear stresses are getting generated, and if we want to know that what amount of stresses are getting generated, that also we can find out. So today we will see all these derivations and procedures. Today we will have lots of expressions, so please write down all the expressions along with me. Then it will help you in solving the numerical problems.
हेलो
Yes.
सर, आप कुछ बोल रहे थे क्या पहले? मतलब
हाँ
याचना बोल रही हूँ मैं।
हाँ, बोलो बोलो। नहीं, एक्चुअली आज आज नेटवर्क का काफी इशू है, तो मैंने वही बोला था कि शेयर दोनों शेयर्स को कि अगर मैं ऑफलाइन चला जाऊंगा तो तुरंत मुझे कॉन्टेक्ट कर लेना
ओके ओके सर, ओके
और नथिंग से।
ओके सर।
ओके। So this is the initial position of this shaft. Here some twisting moment is acting. say the initial position here is somewhat on the outer surface of this shaft. Due to this application of this twisting moment, this position will now go to some new position, say this one. Let us give some nomenclatures of all the points. This is A. Say the initial position was B. Current new position is B dash. And this thing we are looking from this side. It's a 3D view. So if we want to see from this side, so what we will see? We will see a circular cross section, okay, which is having a radius. Now, as the point B, it was the initial point. Now the point has changed to some new position B dash. So here also the effect of that change will come. Say the new position is, as it is written here, B dash. Say the center of this shaft or the axis of the shaft is O. So from this angle, and this is L is the total length of the shaft. This angle, from the definition of the shear strain in our very first chapter after mid-sem, we know that this is the shear strain because the change, the shear strain induced in the length, because length is here where the dimensions is changing in perpendicular or the transverse direction. So this phi, actually this is tan phi, will be equals to this B dash, that is the change in the position by its original length, that is L. From that definition also we have seen that this angle becomes very small. So tan phi can be assumed as phi for small angle assumptions. That means the shear strain or phi can be written as B dash by L. Okay. Now this is the new initial position was B, that is making an angle here, and this is the new position beta dash. Say this angle is theta. So so this theta is nothing but angular movement of radius OB due to the strain in the shaft length. So this theta, the angle which is created by these two positions OB and OB dash, is nothing but the angular movement of the radius OB. So OB now has changed, and the change, it is changed angularly, and that is the angular movement due to the strain which happened in the length of the shaft. So this angle B dash is theta. Now From that figure also we can see that from the arc length, if we know the radius and if we know the angle of the arc, then we can find out the arc length. Now say the radius is here r. So r is the radius of shaft. So this B dash from this figure we can say equals to r into theta. Again, from this part we know the shear strain phi is equals to BB dash by L. So phi, the shear strain, is equals to BB dash by L. Now the BB dash is equals to r theta. So phi can be written as r theta by L. So this is equals to shear strain. Now from the theory of elasticity, if we want to get the definition of G, what is this G? It is modulus of rigidity. So what is the definition? What is the definition of G? Am I audible?
So shear stress upon shear strain.
Yes. Shear stress upon shear strain. Shear stress is denoted by tau
T and phi.
phi. Good. Now this phi we know. So tau by r theta by L, or G equals to tau L by r theta. This can be modified in this sense: G theta by L is equals to tau by r. So the shear stress, the angular movement of the shaft, of the radius of the shaft, the rigidity modulus or modulus of rigidity of the shaft material, length of the shaft L, and the radius of the shaft R, they all are connected using this expression. Let me write down the expression once again. So G theta by L is equals to tau by R. Now the shaft it can be considered to consist of infinite number of elemental hollow shafts, one surrounding the other. And from this expression, we can see that for a given shaft material and subjected to a given twisting moment or torque, this portion will become a constant value. That means the shear stress is, and shear stress upon this radius of the shaft is becomes constant value. That means shear stress is proportional to R. Now, if the, as I told, the shaft can be consist of several hollow shafts, one upon other, and say at any distance the radius is small r. So if this is the shaft, this is, we are considering the circular section, say this is the maximum radius of the shaft, or ultimate radius is R. If there is some point here which is within this shaft area, within this shaft section, cross section, if this radius is R, the shear stress offered by this portion is, say, denoted by Q. That means we can say that when we are talking about the maximum radius, then the amount of stress, shear stress offered by the shaft is tau. But whenever we are in between this center of the shaft and to the maximum point, there also, if we locate any point in between this 0 to capital R, and if we say that the radius of that point or the distance of that point from the center is smaller, that particular point will also produce some sort of shear stress. The magnitude will be definitely less than the maximum shear stress values, that is tau. So from that part, we can redefine this expression as G theta by L is equals to the maximum shear stress at the outer surface of the shaft by the maximum or greatest radius of the shaft, can also be written equal as to Q by small r, where r is a distance of a point from the center and Q is the shear stress offered by that point. Okay, so let me write down here. So R is so Q is the shear stress offered by the point, or say some area which is R distance away from O, or you understand the center point. So this is the ultimatum expression is like that, but also we can use these expressions because these are proportionals, and for a constant material, for a given shaft of given torque, these properties will become a constant value. So eventually both the cases it will be proportional. The shear stress is proportional to the radius. Now, why we are trying to do this? So one thing we are getting here, that shear stress becomes maximum at the outer surface whereas the shear stress becomes zero at the shaft axis. You understand that shaft axis? If we look from this side, the central point of this circular cross section, that is O, the shaft axis is the horizontal distance, is in the horizontal direction. So that central point, if we look from this side, that axis will be represented by a center point of this circular cross section, and that's why I have written it here, that when this R becomes 0, that means the point at the center point, the shear stress becomes 0, and when this small r, it becomes capital R, that is the radius or the outer surface of this shaft section, then the shear stress becomes maximum. Now, so say this is capital R, the greatest radius. Say this is an area. The distance is smaller. The elemental area is dA, and it is offering an shear stress of quantity Q. So Q is the shear stress offered by the elemental area. So if, let me write it again. So Q is the shear stress offered by the elemental area. Now, if we want to see that what is the shear resistance offered by the elemental area is Q into dA, because this is the stress, this is the area. So the shear resistance offered by the elemental area is Q into dA. Now, from the expression we know that Q by R is equals to tau by R, this capital R. So Q can be written as tau into small r by R. If we just substitute these values of Q, tau into R by R into dA. So this is the shear resistance offered by the elemental area. Now, if we want to calculate the moment of resistance offered by the elemental area, offered by dA, then, so this is the force acting on this area, and this moment of resistance by this area at the center point or at the shaft axis will be tau. This is the force and this is the distance. The moment will be acting at the shaft of the at the center of the shaft or the shaft axis is tau into dA into R square by capital R. Simply we have multiplied a small r distance, that is the distance between the force and the point. So we have multiplied that force into the small r value. So total moment of resistance offered by the shaft cross section is, say we can denote it as T is equals to the integration of tau by R into R square dA. Now, that means if we take this part out, this is R square dA. Is this term known to us for a circular cross section? If it is a circular
Polar
cross section,
moment of area.
yes, good. So this is nothing but polar moment of inertia about this shaft axis. This also can be denoted as IP. That means the total moment of resistance offered by the shaft cross section T is equals to tau by R into IP. Or we can rewrite it T by IP equals to tau by R. Again, we know that tau by R equal, yes, okay, tau by R equals to G theta by L. We already have seen it from the expressions, tau by R equals G theta by L. So we can write it as tau by R equals to G theta by L equals to T by IP. So this is the shear stress of the shaft acting on a section of the shaft. This is the radius of the shaft, rigidity modulus of the shaft material, angular movement, length, total moment of resistance offered by the cross section of the shaft, and polar moment of inertia of that cross section, circular cross section, about the shaft axis. About the shaft axis. They all are correlated using this expression. Okay. Now, let me rewrite the formula again. T by IP is equals to tau by R is equals to G theta by L. So the shear stress we know that shear stress maximum for radius R, okay. So if we just take this part, so R maximum is basically the capital R, right? Because that's what the greatest radius R. Again, for R value, the capital R value, that is the maximum radius, shear stress becomes maximum. So if we rewrite this portion, T by IP is equals to tau max by R, or this T equals to tau max into IP by R. In the last class, we have also seen some sort of relationship between this I, moment of inertia, and the distance of the fiber. So here also another terminology can be introduced which comprise this IP and R, and it can be written as ZP or polar modulus. So this T can be written as tau max into IP bar R. This IP upon R can be written as polar modulus or ZP. I am rewriting this part here. So ZP or polar modulus can be equals to IP by R. That means polar moment of inertia of the shaft about the axis, shaft axis, and this R is the maximum radius. If we do this ratio, we can find out the polar modulus ZP. So the T, the moment of resistance offered by the shaft cross section, can be written as T is equal to tau max. We can write this tau as this tau max as tau also, because if any in between value from 0 to tau, we can represent that q. So we can so it is up to you. You can write it as tau or tau max, that is fine. If you are getting the point, that only is important. So this equation can be expressed in words like this: the greatest twisting moment that a given shaft section can resist. So this is the T, this is the total moment of resistance. So the greatest twisting moment, and this is the resistance coming from the inner internal reactions. And why it is so? Because the shaft is acted by some twisting moment. So that twisting moment should be equal to the moment of resistance from the elasticity theory, and also in the last class we have seen the bending moment equals to the total moment. So here also the greatest twisting moment which is acting on the shaft section, that a given shaft section can resist. So whatever they applied, that it should resist, and that is within the elastic limit. And we are still within the elastic limit because we are using the elastic constant G. So this is the greatest twisting moment that a given shaft section can resist, that is T, can be equals to maximum permissible shear stress tau into the polar modulus So this expression can be written in words like that. This is the maximum twisting moment that the shaft section can resist, and that we can achieve by using these two values. One is maximum permissible shear stress and another is the polar modulus of the shaft cross section. So what this polar modulus gives us, so for a shaft of given material, this polar modulus actually it represents a strength of the shaft in resisting torsion. Please note down all those things. So this is the maximum resistance coming from the section that is related from the maximum shear stress and polar modulus. So for a shaft of given material, this polar modulus will tell us that how much the shaft can resist the twisting moment, and that's what it gives us the essence of the strength. So if we want to say that what is the strength of a shaft which is under a twisting moment or torque, so twisting moment also denoted as torque, TORQE, that then we can say that if what is the strength of this shaft section which is acted by this torque or the twisting moment, we have to calculate the polar modulus. And remember one thing, again from the definition we can see that this polar modulus is a completely dimensional properties. So this is also a dimensional property, this polar modulus. R is also, and the radius has a dimensional property. So it has nothing to do with the how much torque it is acting or not. So whatever the cross section we will use as in the shaft, this polar modulus will gives us the sectional properties or the strength, where this torque and the stress, they are connected to each other because these are the applied torque and this is coming from the internal reactions. So let me rewrite all the expressions. Is it seen? It is not. Okay. So let me rewrite all the expressions. So G theta by L is equals to tau by R is equals to Q by small r. Then one more expression we have found out that T by IP is equals to tau by R equals to G theta by L, and this T also can be written as tau into ZP, and this ZP can be written as IP by R. So I have written all the expressions in one page so that you can write it down, because we have to solve numerical problems using these expressions. So we know all the terms here, right? The G is rigidity modulus. This G is rigidity modulus. This theta is angular movement. In radian. L is shaft length. Tau is maximum shear stress at surface. Okay, and is similarly this Q is that shear stress at small r, and this T is maximum torque, that is also a moment of resistance in, normally it is the same unit of a moment, in unit of moment, and this ZP is polar modulus, and this IP is polar moment of inertia. In that moment of inertia chapter, we have defined mostly this polar momentation as a J. So okay, it's a representation, just nothing is different. So if you are comfortable with J as polar moment of inertia, that is also fine. If you want to write it as IP as polar moment of inertia, that is also fine. So no harm in putting in, but use the same unit, same representation throughout your question, your answer sheet. That makes the difference. So please rewrite the entire part, all the expressions, because we are going to solve a couple of numerical problems now, and then all these problems will be useful. Can I go in the next slide, or it will take some time? Shall I go to the next slide?
Yes, sir.
Okay. Okay. So this T by IP is equals to G theta by L. That can be rewrite as theta is equals to TL into GIP. Okay. So this part is a constant for a given shaft. That is, for a given shaft means if the material is constant, if the cross section is the dimensional property L, that is also, if it's constant, it is fixed, and this IP is also the cross sectional properties that are fixed. Then this twisting, the twist, that is the angle change, is proportional to the twisting moment. That is T. But that is only for a given shaft. This twist is proportional to the twisting moment. Now, this GIP, these two terms together, we can represent as, or we can write it as torsional rigidity. So if it is asked in the question that what is the torsional rigidity, so you have to multiply this modulus of rigidity and the polar modulus and the, sorry, not polar modulus, and the polar moment of inertia, and then the value will give you the torsional rigidity. It is similar to as this E into I. So this is for shaft, and this EI is also called, this is known as flexural rigidity. So this is shaft in torsion, and this is used, this flexural rigidity is used for beam in bending. We have done this part. So that case, if somewhere this E and it I, if we multiply these two part, we can say it as the flexural rigidity, and for the shaft in torsion, you say that this is the torsional rigidity, this G into IP. So this is nothing new to nothing new derivation, just we have to multiply these two terms G into this IP. Okay. So now the very last part. So what we have seen that this G into IP can be represented as the torque required to produce a twist of 1 radian for shaft length, for a unit shaft length. How we are getting it? So this is the expression we have used, T into L, G into IP. So this torsional rigidity also has some definition, that it is the torque required to produce a twist of 1 radian for a unit shaft length. So this is the dimension case. So this GIP is equals to T into L by theta. So if we want to produce a twist of 1 radian, this is 1 radian for a shaft length of unit shaft length of 1 meter, then this torsional rigidity will directly give this T. So if this theta value is 1, L value is 1, this GIP is equals to T. That's what it is said, that it is the torque required to produce a twist of 1 radian for a unit shaft length. So this is the definition from this term. And this shaft also, the rotating shaft also produces some sort of power in that case. So if the shaft rotates with this n RPM, what is RPM? RPM is revolution per minute. Means in 1 minute, if the shaft covers, it rotates n time, so that is the revolution per minute. Under the application of this torque T, torque in Newton meter, then the power transmitted by the shaft can be written as 2 pi nt by 60 watts. Where it is coming from? If we convert this revolution per minute, so in the angular speed, where this angular is W is the angular speed in radian per second. So this conversion of this omega, not W, this is omega actually. So angular speed in radian per second. So the conversion between this RPM and this omega is omega equals to 2 pi n by 60. So this is revolution per minute. It is happening 1 minute, and this is radian per second. That's why this 60 comes. And revolution means it is rotating in 360 degree. So that's why this 2 pi comes to make it in radian. So that's why this is the angular speed in radian per second, 2 pi n by 60. So that omega into T, if we multiply the torque into the angular speed, we will get that how much the power is transmitted by the shaft, and the unit will be in watts. Okay, so please write down this expression as well. So this is the power transmitted by the shaft is 2 pi nt by 60, and unit is in watts. So is it okay? If this is, then just I hope you have written all the formulas now, and we will do some numerical problems in the next part of our class. It's a 2-hour class. So let us take the attendance now. We'll have some break as well. Then we'll start for the numerical parts. So any doubts here or any expression you want to write it down, please write it down here. Can I unshare this part now? Then I will again share.
Yes, sir.
Okay, thank you.
Yes, sir.
Okay, okay. So we'll do this. These problems are quite big. So okay, we'll take time and we'll do slowly. So first write down the problem. This problem consists of all the expressions. So all the expressions will need to us. So I have drawn one figure. You can also draw. Then we can start solving the problem. So it is said that a shaft of ABC, A, B, and say C, is of 500 millimeter length. So total length is 500 millimeter. Huh? And 40 millimeter is external diameter. So the 40 millimeter is the external final diameter. It is bored. Bored मतलब bored का meaning होता है कि we have excavated some portion from any material or any sort of things. This is mainly used for soil. So soil boring is called. So the external diameter is bored for a part of its length AB. So this is the length AB portion to a 20 meter diameter. So टोटल 40 मीटर था पहले, अभी इसमें 20 मीटर फॉर ए लेंथ ऑफ ए बी इज बोर्ड, मतलब एक्सट्रैक्ट कर लिया गया, एंड फॉर द रिमेनिंग लेंथ बी सी टू ए 30 millimeter diameter board. So out of this total diameter 40 millimeter, 30 millimeter का एरिया निकाल दिया गया. So now the shaft looks like this. So this is the outer diameter. For this BC length, it is 30 diameter, 30 millimeter, whereas AB length, it is 20 millimeter diameter. So couple of things we do not know yet how we can solve this problem. To do that, let us do a quick problem here. Not here, it's better to go. Okay. So if we have a solid circular section of diameter D, what will be the polar modulus? What will be the polar modulus for a solid circular section of diameter D?
Sir, IP by R.
Yes, IP
that
by
is
R I
no.
know, but what is the
D
expression?
by 2.
Huh? Yes? Somewhat said something. Achha, for IP we need to know this both the things, na? IP and R. So what is IP value for this solid circular section of diameter D? You can say with respect to radius, if you remember that part. What is the polar moment of inertia of a circular section if radius is R?
Sir, 1 by 2 pi r to the power 4.
Pi r to the power 4 by 2, right? So just
Yes.
that changes radius into diameter.
सर d by 2 लिख देंगे ना उसकी जगह.
हाँ, करके कितना आएगा?
1 by 32 pi d cube.
Very good, very good. Pi d to the power 4 by 32, where d is the diameter. For this, this is the polar moment of inertia. What is the value of r for a circular cross section of diameter d?
D by 2.
D by 2. Good. So what will be the value of Zp then, polar modulus?
Pi d cube by 16.
Pi d cube by 16. Okay, now if we have a hollow shaft, circular shaft, Okay, hollow circular shaft where D naught is the outer diameter and DI is the inner diameter. So now we want to find out what is the value of ZP for this hollow circular shaft. How we can do that? What is the IP value here for this hollow portion? So what is the area? How we can calculate the moment of inertia of a hollow circular section? Polar is just summation of that two, na?
So pi by 32 d naught की power 4 minus di की power 4.
Very good. Pi by 32 into d naught to the power 4 minus di to the power 4. This is the polar moment of inertia for this circular cross section. Okay, the in between portion is hollow. Now, what is the R here? Try to think from the definition of R. For this chapter, whatever we have done, so what was the definition of R?
D naught minus di.
No, that's why I told to think about the definition of the R.
D
If
naught
remember,
by 2.
yes,
D naught by 2.
D naught by 2, no. The only one option left is D naught by 2. Yes, yes, D naught by 2. Sorry, sir. I thought DI by 2. Yeah, D naught by 2. Yes. So R is the greatest radius of this section. Here the maximum cross section goes up to for the D naught case. Okay. So as he rightly said, this is D naught by 2. So what will be ZP? It is simple. I am not taking, so pi by 16 d naught into d naught to the power 4 minus di to the power 4. So okay, so I am okay, this is fine. So why I am telling this? Because for this problem we need to know this sort of hollow circular sections where two diameters are given, external diameter, internal diameter. Again, external diameter is 40. And in between the internal diameter is 20. So now we can use these expressions to find out the polar modulus, okay, for this hollow sections where two diameters are given. So I told in that time that we do not know couple of things how we can solve this problem. One thing now we know that what equation we should use. Another part you must be thinking that till now I have not told that if two different shafts are connected to each other, then what will be the criteria for the entire portion? So in this case, the tip is that if a shaft is made up of different lengths like L1 and L2 and of different diameters, that is of varying sections, the torque transmitted by the individual sections should be calculated first, but the strength of the such shaft will be the entire shaft. The strength will be the minimum of the two values of torque. So from this AB, say for AB portion we are getting a value of torque T1, and for BC we are getting T2. Now as these are connected to each other as a whole, when we want to design this sort of shaft, we cannot go with the higher values. We always go with the lower values because that is the applied load. So whenever we are doing a design problem, always we need to go with the lowest value of the application of the load. So minimum of the, so final T will be minimum of T1, T2. So which is minimum, we will use that as the torque or the strength of this entire shaft. Second thing, I can ask you this one. So if this section and this section, they are connected and this is given some applied twisting moment, what thing will be common in both the sections AB and BC? One particular thing will remain common for both the cases. This is torque is coming, separate torques are coming, but we are considering that the T for the minimum part, but by virtue of this connection, one thing will remain unchanged for both the sections. Can you tell that? You can be wrong, no issues. I just want to think that how you can think of this part. So whenever some twisting moment is applied, this shaft will rotate. Okay?
Okay, sir.
Is, and then AB will also rotate, BC will also rotate.
Yes, sir.
Will they rotate in a different, with a different twist angle, or will they rotate with the same angle?
Same होएगा sir.
Huh?
Same angle.
Same angle, because they are connected to each other. So this is, if moving, this AB is moving by an angle say theta, this BC also has to move by the angle same angle theta. Then only the whole shaft will will rotate to some fixed angular distance or movement. So these are the things which we need to apply for this sort of case. So the first point was, individually we will try to find out the torques applied in the individual sections. then we will find out that how much the strength of the section, that will be the minimum of the two things, T1 and T2. And also later on we will try to equalize the angular movement or angular distortion of the AB section with the angular distortions of the BC section, and from that we will get some equations also, and then we can find out the length of the section, that is L1 and L2, then we can find it out. So your first job is, can you say that what is the torque of this AB section? So if the torque transmit applied to that AB section, if it is T1, what will be the value of T1? How we can find out the torque for AB section? Anyone can tell, please, how we can find out the torque in AB section? What is the expression of torque? Is it becoming very difficult? What? T is equals to the shear stress into ZP, na? We know this equation, na? T is equal to tau into ZP. So for this AB section, D naught is 40, DI is 20. Don't forget the unit. So from this, can we find out this ZP? And the maximum shear stress is given. So this is the tau value. Now can we get the torque transmitted by this AB section? Am I audible?
Yes.
Yes, sir.
चलो एक एक करके करते हैं ना. D naught we know 40 millimeter for AB part. DI is 20 millimeter. So what is the equation for this ZP? We have just seen this expression we have to use. D naught we know, DI we know, again D naught we know. So we can find out the ZP. Tau is given here, that maximum is 80 Newton per millimeter square. So just we have to multiply these two and we can find out the torque for this AB part. Shall I do it? Will that help? Hmm?
942000.
942000. Okay. Unit? Unit?
Newton meter raised power 4. Newton mm raised power 4.
नहीं है टॉर्क का यूनिट तो जो दिस से रेजिस्टिंग मोमेंट ना सो टॉर्क का यूनिट आएगा जो मोमेंट की तरह सो फाइनल एक्सप्रेशन जो भी है जो दैट विल कम in either Newton meter or Newton millimeter. So if you use the D in millimeter, it will come as Newton millimeter.
Millimeter से yes.
Newton millimeter. Okay. So let us try then. This expression you have written down now. These all these things. So I am writing here only because those pages are also there. So okay. This is maximum 20 pages. Okay. So I am writing the expressions for now for AB part. So torque transmitted by hollow AB section is tau into ZP tau into pi by 60 d naught into d naught square 4 to the power di to the power 4. D naught is 40 millimeter. Please write down with me. Then you can check it out once again with you. Then you can find it out easy. So this is 20 millimeter. Now tau is given the maximum as 80 Newton per millimeter square. So this T1 is equals to 80 into pi by 60 into 40 to the power 4 minus 20 to the power 4. This is in Newton millimeter.
Millimeter yes sir.
Millimeter because all we have used in millimeter.
Yes sir. Yes.
So now, as he correctly said, so this is 942 500 Newton millimeter is equals to
500
9.
नहीं 0
हाँ
2000 से 500 नहीं है 5 नहीं है सर 0 है
5 नहीं है बट मेरे पास जो सॉल्यूशन है उसमें तो 5 है
नहीं सर 0 आ रहा है सर यहाँ पे तो कल
You are others can all please can also tell me that whether this 500 is or is coming or not.
Sir, 94200.
9 not
500 नहीं है 0
then maybe they have done some mistake. Okay, as of we can ठीक है then 942 Newton meter. This is the coming as T1. Okay, similarly we can do for the BC part. Please tell me the value. I am just clearing some frames so that I can write it down the problem. Okay. Please do the same process and tell me the value of BC.
686875.
Good. So I am quickly doing for the BC part. I am not writing everything. So here D naught is 40 millimeter. Here DEI is 30 millimeter. What is required? Anything? Tau is 80 Newton per millimeter square. So T2 is what is the expression? T2 will be tau in this 80 into pi by 60 into here it is 40, eta 40 to the power 4 minus 30 to the power 4. सही क्या ना? मैंने अभी कुछ देखा नहीं. 80 into pi by 60 into d naught. Yeah. This is in Newton millimeter. So how much the value is coming? 687 something is coming. Again it says 6872 not Newton millimeter. It is coming.
686875.
Acha, ठीक है, that's fine. 687.2 it is shown. Okay, that is in Newton meter. So that is the torque transmitted by the by the hollow shaft BC. So we know the two torques of the individual sections T. So T1 and T2. So T1 is 942 Newton meter. T2 is 687 Newton meter. So from the point I mentioned that we have to take the minimum of these two as the strength applied by transmitted by the total section. So final T will be minimum of T1 and T2 because that is the design parameter we have to use with this part equals to 687 Newton meter. So for the next part of the calculation, we will use this T as 687 Newton meter. That is the strength of the section. So it was asked that find the maximum power. Find the maximum power if the raft can transmit at a speed of 200 RPM. So what is the expression of power? You have written down, right?
2 pi n upon 60. 2 pi n
2
upon
pi n into T by 60.
Sir.
Unit is watts or W. वाट ही लिखो क्योंकि W में तो वो भी आता है एंगुलर स्पीड और काफी सारे, तो वाट्स लिखते रहो, कोई दिक्कत नहीं. सो दिस इज द पावर. ओके, सो 2 into pi into RPM it is said as 200. T is, we know now, we will use this minimum of this. So this is 2 pi 200 into 687 by 60 watt. So how much it is coming?
One 1437858.3.
Okay, here it is something, it is said that
37.
390. Okay, it's fine. It इतना छोटा में कोई दिक्कत नहीं है. So it's watt or 14.39 kilowatt. Okay, so this is what is this? This is the power transmitted by the complete shaft. complete shaft means ABC. This AB and BC मिला के जो complete shaft, the power transmitted by that is this 14 point some 3 or 14.7 whatever that kilowatt. Also, we have to find out that what is the remaining part. So is the part of saying the shaft can be transmitted or this is determine the fine. So we want to know the L1 and the L2, that is the length is not known to us. We only know the total length of the shaft 500, but L1 and L2 are not known to us. So one thing we have seen that we would use the minimum torque that is already has been used in calculation of the power. Now another thing I told you that these two sections AB and BC, they will rotate with a similar angular distortion or similar theta value, similar angular displacement or theta. So how we can equalize the angular displacement of AB and BC? Just 1 minute, let me clear it. Okay. So theta of AB should be equals to theta of BC. How we can do that? What are the expressions we know? T by IP is equals to G into theta by L. So theta is equals to TL by GIP. So what will be then theta AB? What will be this theta AB?
TL1GIB.
T, what is the length of the AB? We have denoted at L1 by, see in this problem no other materials are denoted, so both are same materials, so we are using G and
IP1.
IP1. Say this is for AB part, okay? Because that will be different, na? Our radius and our diameter is changing, so section is changing, so sectional modulus will change. T should have changed, but here we are designing the whole part as the T, so we'll use that T into L2 by G into IP2. So T gets cancelled, G gets cancelled. So L1 by IP1 is equals to L2 by IP2. What is the value of IP1? IP1 means AB. Pi by, बोलो मुझे, what is the value of IP of our AB?
942.
No, not the, okay, pi by 32. Pi by 32.
Pi by 32 D raised power 3. D raised power 4 is it?
Yeah. So 40 to the power 4 minus 20 to the power 4 and IP2 for BC is pi by 32 40 to the power 4 minus 30 to the power 4. Okay. So this L1 by L2 can be written as IP1 by IP2. That means this by this pi 32 will get cancelled. So this will be 40 to the power 4 minus, sorry, 20 to the power 4 by this 40 to the power 4 minus 30 to the power 4. So what is the relationship between L1 and L2? How much it is coming?
48 by 35.
Yes, in point value, if you want to say.
1.37.
Very good. So this L1, the relationship between L1 and L2, now we know that they are having a relation. L1 by L2 is 1.37. So we need one more equation to find out this L1 and L2 value. What is that? What is the another expression we can use for L1 and L2? जो फिगर मैंने ड्रॉ किया उससे कुछ आ रहा है?
L1 plus L2 is equals to 500.
Yes, very good. So that's what I was asking. So, okay, let me clear this part. So L1 plus L2 is 500 and L1 is 1.37 of L2. Now, please quickly tell me the value of L1 and L2.
$210.9.
So L1 is 289.0 and L2 is 210.
Yes, but
10.9.
11, yeah.
211 small.
So this is the answer for this L1 and L2. Problem is not so difficult, but see, all these expressions we know, we have to just apply this part. We have to apply for this sort of a shaft of two different sections. So we have to equalize the angular distortion. And also one important thing is that we have to keep the T as the minimum of this T1 and T2 for the complete section. So these two tricks we need to keep in our mind. Other things are the same expressions which I have written throughout the lecture class. Okay. So I hope you have written the entire solutions with you. Please go through that part. If you have any doubt, please ask in the next class. I will try to answer. Okay.
Thank you, sir.
Okay. Then I am unsharing this part.